SwayamPrabha. Digital India. Educated India.
Hello and welcome to another lecture of this course on control systems. So I'll begin quickly with a recap of what we did last in the previous lecture, which is where we saw the different kinds of time domain responses that different types of transfer functions can lead to, or different types of differential equations can lead to. Of course, what we were considering in all of these cases were the situation where there is no input, so it is basically the zero input response, and we saw how the locations of these poles determine whether the system is so called stable or not, right. So let me quickly flash before your eyes the slide, the last slide that we discussed in the previous lecture, which is the following, right. So we observed that depending on the location of the poles, which are marked by crosses here on this figure, you have the following kinds of responses, time domain responses, right, when you have non-zero initial conditions. So for example, if you have poles on the imaginary axis, not on the zero, not at zero, but on the imaginary axis, other points on the imaginary axis, then you have oscillatory response. On the other hand, if you have a pole at zero, that is the origin, then the constant value of the initial condition is held throughout for all t greater than 0. On the other hand, any pole on the left half plane, the strict left half plane or the open left half plane, leads to a decay. It could be a pure decay or it could be a decaying sinusoid or cosinusoid, depending on whether it's on the real axis, the left half of the real axis, negative real axis that is, or on the open left half plane anywhere other than the real axis, such as these locations, right. Okay, the critical issue here that we observed was when poles happen to be on the imaginary axis. Now if there is a single pole on the imaginary axis, on a particular location of the imaginary axis, we know that it will either be oscillatory in nature, the response that is, or it will be held at a constant value, it will not decay. On the other hand, if there are repetitions of those poles on the imaginary axis, then we run into trouble, and we saw the reason for this was that typically the inverse Laplace transforms of those rational functions lead to responses of the type t to the power k e to the pit, right. Now this k could be any positive integer or even 0 for that matter. So this k basically belongs to non-negative integers, yeah. So this could be any positive on 0, on any positive integer or 0. On the other hand, this pi is basically the location of this pole. So you can easily see that for k, right, when k is 1, which essentially means that you have a repetition of the pole, because k will be 0 when there are no repetitions, right. So when k is 1 or 2 or 3 or any higher value, so long as your pi is on the left half plane, you don't really care, because as we highlighted that any polynomial cannot outgrow or cannot grow faster than the exponential. So if the exponential is the decaying exponential, it will predominate and lead to a decay of the response due to non-zero initial conditions. Now we have been talking a great deal about these non-zero initial conditions, so let us take a quick look at an example. So for example, you have y triple dot t plus a1 y double dot t plus a2 y dot t plus a3 y of t is equal to 0. Why 0? Because remember we are talking about the zero input response, and suppose we have been given like y double dot 0 is equal to, what should I call it, let us say b1 y dot 0 is equal to B2 and y0 is equal to B3. Actually, I should write 0 minus here to denote the initial conditions precisely. Now, when we take the Laplace transform of this, you can clearly see that taking the Laplace transform will lead me to the following. So, it will have s cubed times y of s, where y of s is basically the Laplace transform of yt, right, and then you have s squared y double dot 0 minus, and then you have another minus s y dot 0 minus and minus y 0 minus. That is about the first term, alright. Then you have the second term, for instance, which would lead to plus a1 s squared y of s minus s y dot 0 minus minus y 0 minus, okay. And then you have finally this term, right, plus a2s y of s, right, minus y 0 minus. And finally, of course, the last term, which is, okay, this is it, and finally the last term, which is nothing but just a3 times y of s, and this entire thing is equated to 0. Now, if you want to find out the response due to these non-zero initial conditions, you take out all the terms that I am underlining with blue here to the right hand side, right. So, all of these terms you push to the right hand side, everything basically that bears a negative sign here on this side, right. You push it to the right hand side, collect together all the coefficients of y of s, which will be like s cubed plus a1s squared plus a2s plus a3, which is just a polynomial really, right. Now, you can immediately see that you will be essentially dealing with something like y of s is equal to some polynomial divided by s cubed plus a1s squared, right, s cubed plus a1s squared plus a2s plus a3. Notice that the degree of the polynomial in the numerator cannot be more than 2. Why? Because remember, these are constants, these are just b1, b2, b3, right, and you have the highest degree of s appearing on the right hand side, which is those terms bearing a negative sign on this side underlined by blue here, highest degree is 2. So, this will always be a strictly proper polynomial, right, on the numerator. So, the rational function will be a strictly proper rational function. The degree of the numerator polynomial is always strictly less than that of the denominator polynomial, which basically tells you what the poles are, right. So, therefore, now hearkening back to the slide in the last class, now you can easily see how these correlate to terms like these. You will obviously expand this in partial fractions. So, this will contain, if there are real poles only, this will contain basically 3 terms like a1 by s minus p1 plus a2 over s minus p2 plus a3 over s minus p3, right. Even if they are complex, I do not care, all that I need to bother with is that the corresponding coefficient will also have to be complex then, as we have seen in the previous lecture, right. So, therefore, we at least know how to solve for the, using Laplace transforms, how to solve for the 0 input response of a system, yeah. And we have also seen the beautiful thing that this is always going to be strictly proper. There is a very bad sort of a mistake I have made, please excuse me. So, this coefficient should be actually multiplied with all of them, yeah. So, there should be a box bracket here rather than just, you know, this. So, this a1 gets multiplied with this as well as this, and this a2 also gets multiplied with this, but anyway, that is just a minor calculation, but nonetheless, yeah, it is a sort of a mistake. So, I just wanted to rectify that. However, remember, this 0 input response is not the only response of the system to any arbitrary input. There is also this 0 state response, which is basically the response of the system to the particular input that you apply, all right. And if you think about it a bit, depending on the kind of differential equation you are dealing with, so for instance, if your differential equation were something like this, something like this, okay, containing up to the third derivative of the input as well. Of course, we do not go for the fourth derivative because we know that then the transfer function will be improper, which will violate the tenets of causality as we have seen earlier. So, this is the highest degree of the input polynomial or the numerator polynomial in this case. So, the highest derivative of the input allowable is 3 if the highest derivative of the output, that is y, is also 3 on the other side, right. So, we will only consider such cases. Now, of course, you can apply Laplace transform to both sides to see that this is going to be a biproper transfer function. And what do you do now? So, in case of a biproper transfer functions, it turns out that you cannot just expand it in this form. You will also have something. So, for example, if g of s is say b0 s cubed plus dot 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 till b3 divided by s cubed plus dot 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 till a3, right. Then of course, you cannot expand it in this fashion only, there will be an additional term which will be the quotient, because now remember, since the degree of the numerator is equal to that of the denominator, you can divide this. So, essentially what you will then have is b0 plus maybe some a1 prime over s minus p1 plus a2 prime over s minus p2 plus a3 prime. So, this prime is of course not the derivative, it is just to distinguish it from these a1, a2, a3 that I have written a1 prime, a2 prime, a3 prime, right. Right. So, this is what the partial fraction expansion in such case would be. So, no worries there, you see, even if it is a biproper transfer function, of course you will have to just bear in mind that there will be this quotient term as well apart from these partial fraction expansions. So, that is the only difference, so to say. So, I hope that with this we are now in a position to solve for any differential equation, whether be it the 0 input response or be it the 0 state response. We should be able to effectively use Laplace transform and then finally take the Laplace inverse, because these are straight away can be read from, these forms can be straight away read from a table of inverse Laplace transforms, and we know that corresponding to the inverse Laplace transform of this, we will get e to the a1 prime times e to the p1t as a response, right. So, it all fits in with this picture very nicely, right. Of course, the stability notion that we discussed in the previous class was only with respect to the 0 input condition. We will see shortly in a lecture or two that when we have the 0 state response, that is the response due to the input, then we talk about something called bounded input, bounded output stability. We will not, we will hold back on that discussion for the time being. Now, just before we go into a more practical realization of sorts, let me quickly touch upon another way. Of course, you can see that you can take the Laplace transform of this and get the transfer function corresponding to this system, but that is another way of looking at this. So, look at the initial premise that we had, right. So, we know that y of t is nothing but, if you take 0 minus to infinity, you had g of tau u of t minus tau d tau, right. We know this already for a fact. Now, suppose your input, suppose u of t is nothing but e to the alpha t, where alpha is basically a complex number. What happens then? So, then we see that y of t turns out to be nothing but 0 minus to infinity g of tau e to the alpha t minus tau d tau. So, of course, we can pull out this e to the alpha t outside the integral, yeah, and then we are left with this e to the alpha, of course, with a minus sign, e to the minus alpha tau d tau. But I urge you to focus on this term now. What is this after all? This is nothing but the Laplace transform of g tau, right, with s replaced by alpha. So, this is nothing but essentially e to the alpha t times g of alpha, right. I have just replaced s with alpha, another complex variable. So, it turns out that if your input to the system is e to the alpha t, then the output of that system will be just e to the alpha t multiplied by this complex number. So if this is a complex number, then this has two things. One is of course the magnitude of the complex number, the other is of course the phase of the complex number, right? Yeah. So now I can clearly depict or capture this like a gain term, alright. So what does this gain term do? We will dwell more on this when we cover the topic of Bode plots in some later lecture, but for now it suffices to see that if you want to find out the transfer function of a system, this is another method of doing it. What do? You just substitute the input to be e to the alpha t, of course you can replace alpha with s, yeah. Either you take directly the Laplace transform like we did in the earlier case here for instance, or for that matter for here, of course here the input was 0, so maybe the more appropriate example is here. You can take the Laplace transform on both sides and you can get the transfer function like so by equating all the initial conditions, right, all the initial conditions set to 0. Or you can also try out by applying an input of e to the alpha t. So in strictest sense these are like eigenfunctions, we do not want to call that term for now, forget about it. So you do not have to really tax your memory to remember all that. The point is, if you excite the system with e to the alpha t, you see that the output will be nothing but e to the alpha t multiplied by this gain, which is nothing but the transfer function, right. So if you excite the system with e to the st, then you actually get the transfer function times e to the st as your output, okay. So let us apply this technique here. For instance, you will see it turns out to be the same thing. So there is however something that needs to be said at this junction. You see this response that you see here, what is this response after all? So we have seen that the total response due to a system is 0 input plus the 0 state. Now this response that you see here is neither, yeah, it is only one part of the 0 state response, that is if you set the initial conditions to be 0, yeah, then this response will be sitting inside that response, but this is not the entirety of the response. See, when the initial conditions are 0 and you excite a system with an external forcing function, then the output will contain modes of the system itself, which are intrinsic modes of the system themselves, and also some modes that are introduced due to the input. Now this part is only telling you about the modes that are introduced due to the input, and therefore this is what we shall call as the forced response, yeah. So the forced response is one part of the 0 state response, not the entirety of it, okay. And in case this alpha happens to be purely imaginary, that means you are exciting the system with some sinusoid or cosinusoid, obviously because e to the j omega t, e to the minus j omega t, these correspond to sinusoidal frequencies, right. In that case there will be transients which are not captured in this response, yeah. So this is only going to then talk about the steady state part of the response, and we shall talk about this in further detail much later in this course when we discuss something called Bode plots and frequency responses, but more on that later. As for now, I just wanted to place it in context that this response, do not mistake this for either the 0 input or the 0 state, because it is neither. It is only one part of the 0 state response which we call as the forced response, right. So for instance, here you have y triple dot plus a1 y double dot plus a2 y dot plus a3 y is equal to, let us say, b0 u triple dot plus b1 u double dot plus b2 u dot plus b3 u. So let u is equal to e to the st, all right. Then we know that u dot is nothing but s e to the power st, u double dot is nothing but s squared e to the st, and u triple dot is nothing but s cubed e to the st, right. So what happens to this? Of course we can replace this with, then we have already derived in this part here that it is just the transfer function times this, right. So then when this is the input, we know that y is nothing but, okay, let me call it g of s to be consistent, not h of s. So this is nothing but g of s times e to the st, right. So what happens then? Then y dot is equal to s g of s e to the st. Similarly, y double dot is equal to s squared g of s e to the st. Remember, these are derivatives with respect to time, so the gs doesn't matter, it's just a constant term insofar as the differentiation with time is concerned, right, is equal to s cubed g of s e to the st. Now, plugging in all of this here, what we have is s cubed plus a1 s squared plus a2 s plus a3. You can check that this is exactly what this is going to be, times e to the st is equal to nothing but b0 s cubed plus b1 s squared plus b2 s plus b3 times e to the st. Now, of course, e to the st is a non-singular function, right? You can cancel this on both sides, right? It is never 0, right? E to the st is never 0 unless one of these is minus infinity, right? So we discount that. So therefore, we can cancel it out on both sides, and we eventually end up getting that gs is equal to b0 s cubed plus you have b3 over s cubed plus dot 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 till a3, which is exactly the same as what we obtained. So this is another way of deriving the transfer function, which is just plug in the input as e to the st, right. Okay, so having seen this much, we will call it to a close here. We will no longer dwell on the theoretical nitty-gritties. We have already seen enough number of ways to derive the transfer function. Now it is time to get our hands a little so-called dirty by trying to look at some practical systems. So we will start first with the kind of systems that we as electrical engineers understand the best, which are apparently electrical circuits, right. So okay, maybe another point, another subtle point before that. Yeah, so you see, I have been highlighting a bit on this requirement that people mention about remembering the form of the Laplace transform and the inverse Laplace transform, the form of the partial fraction expansion, right. And I have said that it is absolutely needless for you to tax your memory with those expressions involving derivatives and things like that. All you are essentially doing is equating coefficients, right. So for instance, when I say that you have this g of s is equal to some ps plus q over s minus p1 times s minus p2 times s minus p3, yeah, we just want to write this as a by s minus p1 plus b by s minus p2 plus c by s minus p3, and then we multiply both sides by this common denominator, and we equate the coefficients of s cubed, s squared and s, yeah, and we come up with what the expression should be, or what the values of a, b and c should be in terms of p, q, p1, p2, p3, so on and so forth, right. Now, what if you forget the expression for the standard form for repeated poles, for instance. So suppose you have this 7s plus 8, so suppose you have this 7s plus 8 and let us say s squared plus 5s plus 20 whole squared, alright. So what do you do then? This is like a pair of complex poles. Okay, so this I can leave to you as an exercise. You try this out when there are repeated complex poles. Okay, I will take a simpler one just for the case of illustration here. I will take the same 7s plus 8 divided by s plus 2 squared times s plus 1. Now we know that we have to expand this in the form given by a by s plus 2 whole squared plus b by s plus 2 plus c by s plus 1. What if 10 years down the line you've forgotten the exact way to do this, and by mistake suppose you've missed out this term? A natural mistake on the face of it, yeah, because you see that there are only two types of terms here. One is s plus 2 squared, one is s plus 1. So obviously if you take the least common multiple of these, it will be s plus 2 squared into s plus 1, and you might think that I need not bother about this term. It might happen. Right now you won't forget this, of course, immediately after looking at this lecture, but suppose 10 years down the line you've forgotten. See, you don't need to fret over this. Eventually you will find out your own mistake automatically. That is the beauty of looking at it as equating coefficients on either side. You do not have to bother about remembering these things. How? Now see, if you multiply both sides by this common denominator, you will be left with something like 7s plus 8 is equal to a times s plus 1 plus c times s plus 2 squared. You see, the problem that you will then run into is, on the right hand side you see this is going to be a quadratic polynomial. Yeah, so there will be 3 terms. One is corresponding to s squared, the coefficient of s squared, the others corresponding to s, the others corresponding to the constant, right. On the other hand, you have only 2 unknowns, right. So immediately anyone who has solved simultaneous equations knows that when you have lesser number of variables and more number of equations, you might run into trouble with consistency, right. So it may happen, and in fact it most likely will happen, that you will not be able to choose any a and c such that it satisfies, right. So for instance here, straight away you can see that if you equate the coefficients of s squared on both sides, you end up with c is equal to 0. You expand s plus 2 whole squared, it will be s squared plus 4s plus 4. So the only coefficient of s squared on the right hand side is c, the only coefficient of s squared on the left hand side is 0. So c turns out to be 0. So then you are only left with a. Now can you choose any a such that the coefficient of s is 7 and a constant term is 8? Of course not. Whatever you choose to be the coefficient of s turns out to be exactly the same as the coefficient of the constant term, which is going to be 7s plus 7. So there is no way you are going to be able to choose a and c to satisfy this. Yeah. So this is like an overdetermined system. You have more number of equations, less number of variables to play with. And this is what should tell you, even if you have forgotten this exact expression 10 years down the line, this is what should tell you that you are missing out on this additional term, which is nothing but this b times s plus 2 into s plus 1, okay. So all that I am trying to highlight through this discussion is that you do not need to remember things, you should be able to work it out. Even if you have forgotten how to expand terms like these, you should be able to work it out, okay. So that is one final point I wanted to make before we venture into circuits. So okay, enough discussions on these theoretical parts of how to get inverse Laplace transforms and Laplace transforms. Let us now go into analysis of electrical circuits, okay, analysis of electrical circuits. Yeah. So we already know certain things about electrical circuits which makes our life apparently, or should make our life easier. So let us take element by element. We know that there are basically 3 kinds of passive elements. Passive elements means they do not have any source of energy, okay. They can store energy, some of them maybe, but they do not pump energy in, okay. They are not essentially sources of energy, they are no active source of energy. So we will see that active elements are elements like operational amplifiers, okay. But resistances, for instance, so this is R and you have current flowing through it. Then you have inductors, L, and then you have capacitors, C, right. So these are all passive elements. Now what is the current voltage relationship here? We know that V is equal to I times R. Here we know that V is equal to L di dt, right. And here we know that V is equal to Q by C, where Q is the charge, which is nothing but integration I dt from 0 to t 1 over C, right. So now clearly this is, the ground is perfectly laid here to apply Laplace transforms. So what are we going to do? What we are going to do is quite simply consider this in the transform domain, right. So this relation, if you take the Laplace transform on both sides, you will see it quite simply turns out to be I of s times R, right. No fuss about this, this is just a constant. Similarly, if you take now, so of course let me mark out the polarities here. Yeah. So similarly, if you take the inductor here, right, what is the relation? We can easily see that the relation is given by SL IS. We are ignoring the initial condition for the time being. Later on, we shall see the effect of non-zero initial conditions and how the equivalent representations can be captured through some voltage sources in addition to these elements. Yeah. So what this essentially turns out is that if you look at it in the impedance form, right, this is V, this is like the impedance. So you can replace this with SL, right. By the same token, for the capacitor, you have the current flowing through this circuit, right, and you have, again you can check out the table of Laplace transforms that we had given earlier a few lectures back. Yeah. So here essentially what you have is this term behaving like an impedance, just like we had this term behaving like an impedance and here this term behaving like an impedance. So what we then end up with is the equivalent representation is 1 over SC. Alright. So now, having seen all of this, we are claiming that we no longer need to look at the time domain differential equations in an RLC circuit with a combination of different resistances, inductors and capacitors strewn throughout the circuit. All we are going to do is we are going to replace this, we are going to replace every inductor with SL, we are going to replace every resistor of course with the R that it already had in the time domain, and we are going to replace every capacitor with 1 over SC. Yeah, and then we are going to just write down algebraic equations, right. If you are writing the KVL or the KCL, we are just going to write down algebraic equations treating these as impedance like terms. Yeah, we don't need to bother with solving differential equations or integro differential equations, and that is how Laplace transform makes our life so easy. Before we get into that, a quick recap of what the different types of circuits that we saw. You know, even before you solved KVL or KCL, which is Kirchhoff's voltage law or Kirchhoff's current law, using the mesh equations or the node equations, something that you are already aware of maybe from your 10th standard was the series and parallel combinations, right. So when you have, for example, impedances in parallel, so this is Z1, so on and so forth till you have, let's say, Zn, right. So between these two terminals A, B, you often have this, you wrote this as 1 over summation 1 by Zi, I is equal to 1 to n. In other words, if you were to denote, let Y is equal to 1 by Z be the admittance. The reciprocal of the impedance is the admittance, as we know in an electrical circuit. So the admittance equivalent of this, for a parallel combination, we saw that YAB was nothing but summation YI, of course I running from 1 through n, I belonging to the set 1 through n, right. So that is what the admittance was. So whether you look at it in the admittance form or the impedance form, this is what the parallel equivalent was. So this is, let's say, the parallel equivalent. Similarly, if you have a series equivalent, so these are just refreshers, okay, you already remember, you already know this, you've done these things since childhood, I assume. So for example, if you have Z1, Z2, so on till Zn, right, and you have current passing through this, let's say this is terminal A and terminal B, then you know that ZAB is equal to nothing but summation I is equal to 1 through n Zi, and similarly if you take admittance across the terminals, you will see that the admittance is nothing but equal to 1 over summation 1 by Yi, I is equal to 1 through n. So these are like duals of one another in that sense, right, the series and the parallel equivalents, if you look at the admittance and the impedance relations, and you've done this whether you have given it much thought before this moment or not, but you have done this. So next we bring ourselves to the fundamental question of when do we use Kirchhoff's voltage law and when do we use Kirchhoff's current law. Now suppose you are just given pure series or parallel circuits, you do not really always want to go into the Kirchhoff's voltage law and current law and make those loops or nodes, right. You can always reduce it to an equivalent circuit, equivalent series circuit or an equivalent parallel circuit. But sometimes you have these sources, multiple input sources or voltage sources sitting in between, or maybe some other elements sitting in between, which prevent you from exactly looking at it as a series parallel equivalent, in which case you have to go for these KVL or KCL based methods of solving for currents and voltages. So counterintuitive, or I should not say counterintuitive, quite contrary to the naming nomenclature, yeah, KVL is used to solve for mesh or loop, whichever you call it, currents, right, and KCL is used to solve for node voltages. The reason being that in KVL the formulation is such that your unknowns are the mesh or loop currents, and in KCL the unknowns are the node voltages, right. So by solving it, that is not to say that if you use KCL you cannot solve for loop currents, or if you use KVL you cannot solve for voltages. You can always do that, but then you have to do some extra work. After solving for the KVL equations, you have to probably multiply those currents with some impedances in order to get suitable voltage terms, right. Similarly, if you want to find out, let us say, the currents using KCL, then after solving for the node voltages using KCL, you have to divide them by suitable impedances or multiply by suitable admittances in order to get those suitable currents. Okay, so KCL is applied when you want to determine node voltages, KVL is applied when you want to determine the mesh or loop currents. Okay, right. So nothing works better than, say, an example. We will take the most obvious straightforward example, the series RLC circuit, right, and we shall go about this and solving and see how this actually helps us in solving for an actual differential equation, right. By the way, just another refresher before we get into that, whenever possible, if you are using, let us say, if you are using the KVL, right, if you are using the KVL, then this is the sort of voltage sources you have, the non-ideal voltage sources, right. So if you want to apply KCL to the same circuit, what you generally do is you convert it to an equivalent current source like so, which is given by I is equal to V over Z, right, and you put this same impedance, yeah, like this. Just a refresher of circuit theory basically. So if you are given a current source like this, you convert it to its voltage source by multiplying the current with the impedance in parallel and assigning that magnitude to the voltage source and putting the impedance in series. If you want to apply KCL to this sort of a circuit, you'd better, of course this is not to say that you cannot apply KCL to this, you can, but it makes life easier if you convert this to its equivalent current source, right. So this is just again another quick refresher of some basic idea that you are already familiar with. So again, without further ado, let us move into this circuit, the series circuit that we promised, R, L, C, okay. And suppose we want to, so I'll use the Laplace transform domain, so I'll change this to V of S, I'll consider this current to be I of S, and suppose I want to determine the current that is flowing through this, I want to solve for I of t. So the idea is to solve for I of t, say when V of S is 1 by S, which is a step input. Okay, so how do you go about this? Now you will see the actual power of this Laplace transform. You will see that we can write in the impedance form. So this voltage is balanced by R times I of S plus sum of the voltage drops, right. So this is R times I of s plus SL times I of s plus 1 over CS times I of s, right. So after a bit of algebra, you will see that you immediately come up with I of t is nothing but the Laplace inverse of the following term, and you will see in a moment why I am writing it in this fashion. It is just 1 by L over s squared plus R by Ls plus 1 over Lc, okay. Yeah. So basically, and of course we will have to have this 1 over s. Why? Because remember, this Vs is a step input, so its Laplace transform is 1 by s, so this has to be there, right. So this is what we are interested in determining. Okay, let me make it a little simple here. Let me just say that we are trying to determine the impulse response. So let me make it 1 over here, because we will deal with this step response later in a later chapter in further detail. Okay, for now let us just say it is the impulse response. So you know that the inverse Laplace of 1 is basically the delta function, right. Okay, so having seen that, let us get into the next page and see what this essentially leads us to. So what we are then trying to find out is, recall that it is the Laplace inverse of this, but we want to massage this into something that we are familiar with, that we can read off directly from the table. So we want to get it into this familiar form. That is the reason why we made this adjustment here. So this is basically going to be our omega n, this is going to be our a, right. So this is omega n squared, so this is s plus a squared plus omega n squared. We have got it exactly in the form that we want it to be. So now what we need to do is we need to push in this L inside this. So what we will then have is 1 over square root of, what will it be? Okay, maybe I have made a mistake here. It should not be this square root sign here. Yeah, the square root sign should not be here. It should be just 1 by Lc, like here, right. So we push in this L here, so you get L squared here. So what we will then have is L over C minus R squared by 4 times, now we can straight away read off, you see, the inverse Laplace of this, which is nothing but e to the minus RT by 2L, yeah, this is plus a, so e to the minus a t times sine of square root of 1 by Lc, which is the omega n, yeah. So our omega n is 1 by Lc minus R squared by 4L squared whole under square root, yeah. So this is going to be our zero state response for the circuit, and all of this we have done without trying to solve for any differential equation, okay. So this in itself should convince you about the power of this Laplace transform equivalent, okay. So if you are working in the Laplace domain instead of in the time domain, we can bypass this arduous task of having to deal with differential equations, right, and just focus on some algebraic manipulations. I must warn you, however, that if you want to solve for the zero input conditions, then remember the Laplace transform method only works when all of your variables and their derivatives are given at the same instant of time, which is every or one of their values are specified at 0 minus, t is equal to 0 minus. In a general differential equation, you might know the current at 0 minus, you might know the derivative of the current at some other time instant, you might know the second derivative of current at some other instant. In such cases, the Laplace transform method will not help you, and you will still have to resort to the classical method of solving differential equations. So that is just one caveat that you should bear in mind before thinking that the Laplace transform is really the all powerful method that we have just taught you, okay. So now, having seen this, we will get into a slightly more involved or complicated example of a circuit, alright. So let us for instance take another circuit that looks like this, and this will justify to our minds, that well, the Laplace transform does indeed help our cause. In case some of you might have felt that this is after all a well known differential equation, we could have done it by the classical method. I mean, it's not as if the Laplace transform has drastically reduced our effort, because after all we've had to do all of this algebraic manipulation. But now this example should hopefully convince you about the power of Laplace transform. Okay. Okay, good. So here we have another 1 Henry inductor, and okay, and here we have a voltage source given by V of t, right, and here we have another inductor. This is fun. Now what do you do? Now suppose the variable that you have to find out is this, the V out. So determine V out, okay, as a function of time, of course. How do you go about this? Now you see, if I were to just consider the transformed equivalent of this, let me draw that with the blue ink. So this is just going to be S, right? This is going to be 1, this is going to be 1, I am dropping the units. This is going to be S again, this is also going to be S, and here you have V of S, right, and let me use just KVL this time, okay. I know it's a voltage that you've been asked to find out, but okay, it doesn't matter. Maybe I'll leave the KCL application to you as an exercise. So I'll solve it using KVL, you solve it using KCL, or we'll see if we have time we can actually show you the equations for both. Alright, now what do we do about this? Let us assign these currents here, let's call this I1, let's call this current I2 like we do in KVL, let's call this as I3. If you want to write out the equations now, look at this first mesh here, the voltage on one side must be balanced by, what is the current flowing through this? It's I1 minus I3, I1 minus I3, again I am dropping the S for brevity, I1 minus I3 times 1, so I am not writing it down separately, plus what is the current flowing through this? It's I1 minus I2, so S times I1 minus I2, that's equation 1. Equation 2, in the second loop there is no voltage source, so you have 0 on one side, on the right hand side it is balanced by, what is the current flowing through this? I2 minus I1 now you are taking it in this sense, so it's I2 minus I1 times S plus I2 minus I3 times 1, I2 minus I3 times 1 plus this, there is only one current flowing through this, that is I3, so it is S times I2, not I3, this is I2, so it is S times I2, this one, okay. Now we consider the third loop, so name this equation 2 and we go on to the third loop, again there is no external voltage source, so look, through this there is only I3 flowing, so let me just write down that SI3 first, and then through this I know that there is I3 minus I1 flowing through this element times 1, so I do not need to write anything, plus this is again I3 minus I2 times 1, I3 minus I2 times 1, right. So these are the three equations. So of course now we have three equations, three unknowns, we should be able to solve for them. This is of the form Ax is equal to B, where A is basically 3 by 3, B is 3 cross 1, so it is exactly in the same form and this is my unknown. You treat this S like a coefficient like you do for real numbers, treat this like a number for the time being, and then you solve using Cramer's rule, alright. You can solve for this using Cramer's rule. Before that, however, I want to show you another simplified form of this equation which will enable you to read off these equations even without having to write down so carefully. Like here you might have noticed I was keeping track, right, I was keeping track of the currents flowing through these individual elements. But now if you keep track of, if you notice this pattern that I am going to just show you now, right. So I am going to just write this equation 1 in a simplified way, and you will see that I do not need to bother with even looking at the circuit in detail. What am I going to do now? So I am going to write this I1 times something plus I2 times something plus I3 times something. Then 0 is equal to I1 times something plus I2 times something plus I3 times something. And the third equation I am going to write as I1 times something plus I2 times something plus I3 times something. Now you see, by visual inspection I am going to write down what these somethings are that I have just denoted here, even without having to carefully read off. How so? Here is what I am going to do. So in the first equation, which is corresponding to loop 1 whose current is I1, what I am going to write for the coefficient of I1 is the sum of all the impedances in loop 1, which is S plus 1, right. So I am going to just write S plus 1. Similarly, in the second equation with respect to loop 2 where the current is I2, I am going to just sum together the impedances in loop 2, right. So this is 2S plus 1. So this is 2S plus 1, sorry, not there, in the second equation, I am sorry, this is going to be 2S plus 1. Similarly, in the third equation, I am going to just look at I3, this is S plus 2, S plus 1 plus 1, so it is S plus 2. So I am going to just fill this up with S plus 2. What about these other terms? Of course, they will appear with a minus sign. So let me put a minus sign next to each of them with a minus sign, and what is going to come inside? So you see, in the equation for loop 1, the coefficient of I2 will be nothing but whatever element is being shared between loop 1 and loop 2. So what is being shared by loop 1 and loop 2 is this S. So I am going to just write this S here. Similarly with I3, what is common to loop 1 and loop 2? Just this resistor 1, so it is going to be just 1, yeah. So I am going to just write 1 here. By the same token here, I can write this the coefficient of I1 as whatever is common between I1 and loop 1 and loop 2, which I already know, right. I already know that this is going to be S. See this pattern that emerges, yeah, loop 1 and loop 2, and similarly loop 2 and loop 3, what do they share? Loop 2 and loop 3 share this resistance, so it is going to be just 1. So this is going to be just 1. By the same token here now I am going to just write 1 here and 1 here, right. So this is going to give me my 3 equations, 3 unknowns, right. So if I apply Kramer's rule, I urge you to check that you can actually evaluate this. So I have done this, I am going to just write down the expression. Remember, I have to solve for the voltage across this inductor, for which I need the current I2. So if I solve for I2, I am just going to multiply it by S and I am going to get the voltage across this inductor, right. So I am going to just get this I2S, just apply Kramer's rule, which is pretty straightforward really, and then you would know. So let me just do a footnote sort of a calculation here. So basically what we are trying to determine is S plus 1, this determinant minus S minus 1 minus S, 2S plus 1 minus 1, S plus 2 minus 1 minus 1. This is the determinant. So we want to evaluate this determinant equal to some function of S. So this is going to be the denominator, and then if you want to evaluate I2, you just replace this column. So you replace this column by Vs 0 0, right, and you get the second determinant. So you divide the second determinant. So this you call as, let's say, delta. So you divide this determinant of S plus 1 minus S minus 1 V of S 0 0 minus 1 S plus 2, this determinant to divide by delta, and this is going to be your I2, yeah. Once you have got I2, you just multiply it by SI2, S, right, to get SI2, which will be nothing but your output voltage that you want to actually evaluate, alright. So I think I have already tried this out in rough, and here is what the solution comes out to be. Let me just write it down. So I2 is going to be nothing but s squared plus 2s plus 1, unless I am much mistaken, please check the calculation, this can also be a nice exercise for you, by s squared plus 5s plus 2, right, times v of s, right. So now when you multiply this by s, you have v out of s is equal to s squared plus 2s plus 1 upon s squared plus 5s plus 2 times v of s. Now depending on whatever input signal is being given, right, this v of s, have I called it v in? No, I have called it vs, so it is fine. So whatever is the Laplace transform of that signal, you apply it here and then you apply inverse Laplace transform to this in order to get v out. So v out of t is going to be nothing but the inverse Laplace of s squared plus 2s plus 1 divided by s squared plus 5s plus 2 times v of s. In case someone wants you to just find out the transfer function for the circuit between v out and this v, then it is just this term, right. So this term is exclusively your transfer function, okay. So in the next lecture we shall see the analogy between this method that we have used here, the KVL. We have shown you a shortcut. One, of course, we have shown you how you can write the KVL equations by just replacing the elements by their corresponding transformed variables, that is SL for L and 1 by SC for C. And then we have also shown you a shortcut where you can just read off the entries of this AX is equal to B sort of matrix, yeah, what these cross terms are and what these diagonal entries are, by just looking at the circuit by visual inspection. It is very straightforward. We will look at similar analogies when we are applying it to KCL in the next lecture. So hopefully you have enjoyed this, looking at these known things in the perspective of something hopefully new and fresh, and this should also help you maybe in your course on circuit theory that you might have already undergone. Thank you all.